So we're going to continue with 5.3 double angle formulas, which is another set of commonly used identities, similar to the sum and difference formulas. The identities are shown in the box here, and you can see that we've got three different identities, one for sine, another for cosine, another for tangent. The one that you're going to use the most will be the sine 2a equals 2 sine a cosine a. So we'll really keep an eye out for that as you're working through the problems. Also notice that the cosine 2a has three different versions. So just make a note of that. If you replace cosine squared a or sine squared a with its associated Pythagorean identity, you get the three different versions. So if you replace cosine squared a or sine squared a with your Pythagorean identity sine squared a plus cosine squared a equals 1, you will get the other two formulas. A couple of notes about the algebra on these. If you look at the left side here, does sine 2u equals 2 sine u? Is that a true statement? Can we pull the 2 out from the inside? You know, kind of like we're just rearranging almost algebraically, like we might do in an algebraic expression. Well, let's check it. Let's just pick an angle. So let's try u equals pi over 6. And when you plug in sine of 2 pi over 6 equals 2 sine pi over 6. We'll put a question mark there because we're not sure that it's going to work. And then we simplify this and replace those with our exact values. Sine of pi over 3 gives us root 3 over 2. And on the right side, sine of pi over 6 gives us 1/2. And that's not a true statement. That's false. So it does not work. And so, again, you have to be really, really careful with these. You can't just take constants and move them around. These are functions. This is not sine times 2 times u. It's sine of 2u. And because of that, you have to use the identities that make those statements true. Now, if we did sine 2u equals tangent 2u equals sine 2u over cosine 2u on the right side here, as we can see, though that actually is a true statement, and we've seen that before. So as long as the angles are the same, then the identity can be scaled up or down. So it's really equivalent to doing, tangent of t equals sine t over cosine t. Same thing. Now we'll employ some of the strategies that we used in 5.1, 5.2, especially 5.2 with our sum and difference formulas to solve problems finding the exact values given certain clues. So if you take a look at example 1, we're given cotangent of b equal to -5. We're given that that angle b is between 3 pi over 2 and 2 pi. So we're in the fourth quadrant. And we need to find the sine of twice that angle, tangent of twice the angle, and cosine of twice the angle. So if we wanted to find the sine of 2b, then we would employ our double angle formula for sine. So sine of 2b equals 2 sine b cosine b. But we're not given sine b or cosine b. We're only given the cotangent of cotangent of b is -5, and we're given that it's in the fourth quadrant. So we'll use the same strategies as we've used before for this. The best thing to do is to use the clues to make a triangle. And that triangle represents all of the ratios for our angle. And so this is our angle B. We've got cotangents is equal to -5. So I would rewrite that as a fraction, -5/1. And so we would have the adjacent side is 5 and the opposite side is 1. Instead of opposite over adjacent for tan, cotan would be adjacent over opposite. Now I've got that negative sign, so I need to make a decision about where the negative sign goes. In the fourth quadrant here, I'm dealing with the positive x-axis, the negative y-axis. So the 1 is going to be the negative part of the ratio. So even though it says -5, make sure you just take the negative and put it with the appropriate side on the triangle. So then given that, now you have all of the information you're going to need to be able to get sine, cosine, or tangent of just the regular angle. And we'll need the hypotenuse, of course, using the Pythagorean theorem. 5 squared plus -1 squared gives you 26, and then you take the square root. And that's always going to be positive. So the sine of angle B then is going to equal -1/√26. The cosine of B is going to equal 5/√26. And the tangent of B is equal to -1/5. And what I would do for now is I wouldn't rationalize these yet because you're going to be doing a lot of multiplying of fractions. And so let's just see how that plays out. So now we can replace then our sine B and cosine B in the formula. And when you simplify that, you can see actually that it's probably a good strategy to just wait before you rationalize, because when you multiply across in the numerators, 2 times -1 times 5, that gives you -10. And in the denominators, square root of 26 times square root of 26 just gives you 26. And that all ultimately reduces to -5/13. Always simplify to lowest terms. If you do end up at the end with a radical in the denominator, then you would rationalize it. So you've got one option for doing sine 2b. You only have one option for doing tangent 2b. So go ahead and do the substitutions, and I want you to try working through the fractions and the simplifying on your own. Pause the video and then check your answer with mine. So I'm going to replace this with tan b, which is 2 times -1/5. 1 minus tan squared b. Make sure you put that -1/5 in parentheses so that you get your order of operations correct. The numerator simplifies to -2/5. The denominator gives you 1 minus 1/25. which gives you -2/5. 1 minus 1/25. Well, that's 25 over 25 minus 1 over 25 is 24 over 25. And then when you simplify that, I'm just going to invert and multiply. Clean things up. And you end up with a -5/12 for B. Now for C, for cosine 2B, you actually can choose any of the three formulas to work through this. Just pick one and plug it in, and we all should get the same answers. I typically use the first one, and I'll explain why, but you can choose any of them, so go ahead and try that, pause the video, and then check your answer with mine. So the reason why I'm choosing that first one is because then they'll automatically have common denominators when I plug in the fractions. I've got 25 over 26 minus -1 over radical 26 squared just gives me 1 over 26, which gives me 24 over 26, or 12/13. So that little triangle method, drawing that thumbnail sketch, is really a great way of unpacking the situation like this. So if we take a look at example 2, we've got a question that asks us to find the exact value of 2 tan 15 degrees divided by 1 minus tan squared 15 degrees. Doesn't look like anything that we've done before. 15 degrees is not even one of our common unit circle angles. So this is about really getting to know the formulas and recognizing a connection between what you see there and above in your box for tangent. You'll notice on that relationship, that expression is basically the right-hand side of the formula. So we're going to notice that tan of 2b is equal to twice tan b divided by 1 minus tan squared b. So it's kind of interesting. You see that 2 moved out from the b, but it's divided by 1 minus tan squared b in order to make the relationship true. And so if you also notice here, we're talking about twice b and a single b. So if b is equal to 15 degrees, then 2b would equal 30 degrees. So really, then, this becomes tangent of twice 15 degrees is equal to 2 tan 15 degrees for 1 minus tan squared 15 degrees. But we don't know the exact values for the tan 15, but we do know the exact value for tangent of 30. So ultimately, then, we can actually get the answer for that complex expression by working on the left side. Tangent of 30 is root 3 over 3. So just working in reverse in this case, and then using your unit circle exact values. So before we move on, I'm going to give you a little tip on dealing with tangents in MyLab. So if you're calculating in a problem the sine of 2a, the tangent of 2a, and the cosine of 2a, if you do the sine of 2a and cosine of 2a first, then you can use your reciprocal identity. So you can do 2a or tangent of 2b, whatever your variable is. We can take the result of sine of 2b and cosine of 2b and divide them and simplify. And that will oftentimes be a much cleaner way of getting at the tangent rather than plugging in the standard tangent formula. Also realize that these double angle formulas can be scaled up. So if you have a double angle combination, say you want to do the sine of 4a, you can scale it up from 2 theta, or 6 theta can be scaled up from 3 theta. So just, if you look at the formula below, this is really twice 2 theta. So you're just doubling all of the angles from their original angle. And then here, you're doubling 3 theta. So as you can see, you've just really tripled all of the angles in the formula, and so you can scale those up to create a lot of different other identities. Now, most of the problem solving in MyLab is computational. The other part of your assignment is working through verifying identities. So we'll do that with some double angle examples. One thing that we've seen before, especially when we were doing even odd, was that in order to collapse and rearrange and combine user identities, we had to be working with the same angle. So if we've got tan theta equals sine 2 theta over 1 plus cosine 2 theta, can't do much with this until everything is in the same angle. So we'd either have to scale up to get a tan 2 theta, which is not real obvious, but we could use our double angle identities to expand the right side, which I would consider the more complicated side. So what I'm going to do here then is replace sine 2 theta with 2 sine theta cosine theta. And then I need to make a decision. We've got these different options in the denominator for replacing cosine 2 theta. And ultimately, to get tangent, we want sine divided by cosine. So I'm thinking maybe if I could cancel out a cosine, so maybe stick with the cosines. And we also need to get rid of this 1. So I'm going to replace cosine 2 theta with 2 cosine squared theta minus 1. And then when we'll clean up the denominator. And when you simplify the denominator, you get 1 minus 1. And then you end up with 2 cosine squared theta. And this looks like it's going to work out pretty nicely. 2's cancel. We're in multiplication here, so you can cancel terms out. So you end up with sine theta divided by cosine theta. And remember, this needs to carry all the way down. When you're writing these out, you need to write them vertically, not in one row. Show them step by step. You're writing a mathematical proof here. We'll let you do a shortcut with the arrow. Let's take a look at B here. We've got, it's a little different. We've got sine of 3 theta, which we haven't seen before, and that would be double an angle of 1.5 theta. So that seems a little bit maybe an odd way, and it doesn't really even match up with the right-hand side. So that little trick from above here doesn't seem like it would work. So the hot tip on this one is to actually go back and use your sum and difference formulas. What you can do is then actually work from the left-hand side. Sine of 3 theta, and let me just rewrite this. Can be written as the sine of theta plus 2 theta. And then we'll leave the right side alone. So this is one of the rare occasions that we're going to work with, going to decide it's not multiplication or subtraction, addition. But the reason why is the 3 theta makes it the more complicated side. And then from there, what you want to do is you're going to expand this using your sine of a plus b formulas. So take a minute, expand that left side, and then we'll see what we need to do to continue breaking it down so that we can get this right-hand side. All right, so given this, making some progress, we need 3 sine thetas on the right. We need 4 sine cubed thetas. But now we've got these double angles. And we need a bunch of sines. So if you have an idea, plug it in and keep going, and then just check your answer with mine. If you're not sure, what I would suggest doing is replacing both of those double angles with their counterparts that use as many sines as you can get. So for example, I'm going to replace cosine 2 theta with 1 minus 2 sine squared theta. And I don't have much option with the sine 2 theta. So pause the video and keep working through it. I think you can finish it from here. So now I'm going to distribute for both of these. And we're almost there. I'm going to replace that cosine squared theta then with our Pythagorean identity. This one is truly a tour of the entire unit so far. And distribute that to sine theta. And let's see what we've got left then. We've got a sine theta that's going to combine with 2 sine thetas. That means you have 3 sine thetas. And then we've got a negative 2 sine cubed theta and another negative 2 sine cubed theta, which are going to combine to give us the result that we want. And we'll close out with a final statement showing the equality of those two. So let's continue with those strategies, really using everything that we've learned in Chapter 5. Cosine 4t, that is, we're basically scaling up then the cosine 2t formula. Notice the right-hand side, it looks like that could be something that you could factor. You could factor and then convert it into something related to cosine 4t. That would work. But again, this is another example. If you have a scaled up identity, it's pretty easy actually to scale it back down. And so I am going to work with the left side. I consider the cosine 4t the more complicated side. Now the way that I would write that let's start by rewriting the problem. And I'm going to replace cosine 4t with cosine of twice 2t. And leave the right side alone. And then I can put in my double angle formula, but remember my angle is going to be 2t rather than just t. So you look at your double angle formulas, and where you have these a's, you would just plug in a 2t and just chunk it together like that. So I would write this, and I'm going to choose, because I'm dealing with all of these cosines over here, I'm going to pick the version of the double angle formula for cosine that has the cosines in it. I'm not going to have any sines in mine, because I don't think I'm going to need those. So I would write this would be 2 cosine squared 2t minus 1. Again, just placing that a with a 2t. And then I'm going to, I've got to expand this out to get cosine to the 4th t's, and I've got cosine squared t's. So what I'm going to do here is look at this a little bit different way. I'm going to make this 2 times, and actually I'm use a bracket, cosine of 4t quantity squared minus 1. Cosine squared 2t is, whoops, that should be a 2t right here. So I'm just moving the squared symbol to outside, which is what you're doing when the cosine squared 2t is the short form of what I have just written here. And then what I'm going to do is replace cosine 2t with 2 cosine squared t minus 1. Squared minus 1. So I've taken, here's my identity here, because I'm trying to get, again, I'm trying to expand it out to get these. We've got 8s, we've got cosines to the 4th, so I need to kind of break it up. And now what I can do is multiply it all out and FOIL it out. I still have a 2 out here, but when I multiply 2 cosine squared t minus 1 by itself, I'm going to get 4 cosine to the 4th t. The inners and outers are going to give me minus 4 cosine squared t, and the last would give me plus 1, like this. And now you can see I'm getting pretty close. So now I can just start, pull the 2 on through. So I've got 8 cosine to the 4th t minus 8 cosine squared t plus 2 minus 1. And we are almost there. We just need to combine the plus 2 and minus 1. And so now I will just clean up the left side. 8 cosine to the 4th t minus 8 cosine squared t plus 1 equals the same thing on the other side. And there's our complete proof for that. So there's a lot of different creative ways that you can combine. You just need to try stuff. And these are a little bit more complicated, so I'm kind of modeling some representative strategies here that will help you work through some similar ones in the homework. Another way to verify identities is actually using graphs. It says that half of an identity and the graph of this half are given. Use the graph to make a conjecture as to what the right side of the identity should be, then prove your conjecture. So take a second to look at that graph and decide what shape that graph looks like. You can see that it goes through 0, and it is an increasing graph as you're moving from 0 to 2. That looks like a sine graph. So let's see how that plays out if you were to actually complete the identity. And to complete the identity, what I'm going to do is just expand that left-hand side. So sine 2x is 2 sine x cosine x, and secant is 1 over cosine. So as you can see, when I simplify that, I end up with 2 sine x. So that must mean that the right side of this identity is going to be 2 sine x. And if you look at that graph, it's a sine graph, and it has an amplitude of 2. So that checks out. Our last problem is a practical application. Example 5 gives us the formula used to predict the landing distance of a projectile. It's written as d equals v naught squared sine t cosine t divided by 16. The t is the angle in degrees in which the object leaves the ground. The d is going to be that horizontal distance from the initial point to the landing point. V naught is the initial velocity in which that projectile is launched. And this formula is designed actually with the constants to give a distance in the units of feet, but our problem is in meters. So we're going to do an alternate version of it. D equals V naught squared sine t cosine t divided by 4.9. And this is the metric version of that same equation. So our goal here is to find the initial velocity. First of all, it's to express the formula using an identity, and then find the initial velocity that produces a distance of 17.3 meters for the angle of 60 degrees. I'm going to start by rewriting our formula. D equals V naught squared sine t cosine t divided by 4.9. To write this as an identity, the only identity that really directly connects to sine t times cosine t is our double angle formula. But the double angle formula for sine 2t has a 2 in front of it. So what we're going to do is we're going to multiply the top and the bottom of this equation by 2. And then that way we can take the 2, the sine t, and the cosine t and chunk them together, leaving the v naught squared out in front, and then writing the rest of it as sine 2t. And then in the denominator, you'll get 9.8. And physics students will recognize that. That represents 9.8 meters per second squared, the acceleration due to gravity near the surface of the Earth. So that if we replace the d with 17.3 meters equals v naught squared, and then we're going to plug in 2 times 60 degrees, divided by 9.8. Now we just need to work through the math to get the velocity. So work through the operations on this and solve for V naught, and pause the video and then check your answers with mine. I'm getting V naught squared equals 195.8. So V naught would equal plus or minus the square root of 195.8 or plus or minus 14, and those units would be in meters per second. Now, of course, in this case, we're looking at the velocity here. The signs for this have to do with whether you're going a positive and negative direction. And for our purposes in our homework assignments and in my lab, we're just going to use the positive case, a positive velocity. So V naught would equal 14 meters per second. And we can actually check that with the simulator that was used in the diagram. We go in and we have the bullseye set at 17.3 meters. If I move the initial speed to 14, and we're going to actually fire, let's see here, we had the girl there. We can fire the girl. She would be the human. And hit fire. And there she goes and lands right on the bullseye. Now what's interesting about this is there's actually another angle that will enable her to hit the bullseye. So I want you to think about what that might be. It's actually going to be an angle that is lower than 60 degrees. If I lower the cannon actually to 30 degrees and fire, she's not in the air for as long, but she actually lands on the bullseye at that same distance. If I pick any other angle and fire, see there, she's going to be, it's a little too far. If I go a little bit higher, she's going to land a little bit too short. There's always going to be two angles that hit the bullseye. And what's interesting was 30 and 60 degrees, those angles are complementary angles. So we're just going to make a little note here. So there are two angles that produce the same D. And those two angles would be T equals 30 degrees and T equals 60 degrees. They're complementary angles. And the reason why that works is because the sine of 2 times 30 degrees and the sine of 2 times 60 degrees, well, that gives you sine of 60 and sine of 120. These are equal to each other. So they'll end up giving you the same distance. So that's it for the 5.3 notes, and these notes will be posted on OneDrive.